Hi, we've done a large number of videos on sound. In our last video, I covered some unusual materials that can be used to construct sound-absorbing panels for your studio or your home listening room. I covered the effect of helium on speaker operation and some techniques and construction materials to build speakers, speaker enclosures. We gave you a tour of our anechoic chamber upstairs. And in previous videos, we covered our DML or distributed mode loudspeaker panels, as well as the construction of our Voight tubes. We built an active sound reduction chamber, and in all of these videos, we've always focused on quality, finesse, keeping things quiet and under control. But you got to admit, size does matter. And in this video, what we're going to do is we're going to kick the volume up a notch, and I'm going to show you how we constructed our own DIY LRAD system. Ready? It works. And so now what we're going to do is I'm going to go inside and I'm going to show you how to put this together. Let's go. So LRAD stands for Long Range Acoustic Device. It was a term that was coined by a company that's now called Genesis. And I think a more appropriate designation would be Long Range Acoustic Projector. But LRAP doesn't sound as good as LRAD, and I'm sure that's why the term stuck. There's another company called Hyperspike, which also manufactures a similar device. And I first became aware of these systems in an old television show called Whale Wars, when the whalers were using these to deter interference with their operations. And they've become a lot more notorious in the last few months because of all of the enthusiastic outdoor activities that are occurring in a lot of our major cities, especially here in the US. But these devices don't always have to be aggressive. They can be used as portable public address systems. In addition, they can be used for search and rescue. You mount one of these devices inside of a helicopter, and then you can announce to, the lost hikers, please stay near the road. Help is coming. Maintain social distancing. But in any case, their popularity or their notoriety is primarily because of the deterrence nature of this high volume sound, a non-lethal deterrence. I thought at first, when I first looked at these devices, and you might have thought the same thing, that they were based on what's called a phased array. They're very flat and thin. The impression, I don't think, holds up to some of the evidence that I've discovered when I was doing the research for this. First of all, there was a video that was produced a couple of years ago by a gentleman that purchased one of these older LRAD units on eBay and tore it apart. And we'll put a link to that video in the description below this one. But when they opened it up, apparently what we had was just two folded horn speakers in a mil-spec type of housing, but it was pretty simple. And when you look at the Hyperspike systems, you can even see in some of their models they have sort of a cloverleaf pattern typical of, say, 4 horn speakers. When you look at the specs for these devices, they have a sound spread or distribution of sound that's typical of a horn speaker, 30 to 45 degrees. And the effective phasing, although it's significant, very significant, and I'll talk about it in a sec, it is, I believe, a secondary effect, because When a phased array is used, say with radar in an airplane or sonar in a submarine, effectively you have a large number of emitters or transducers, and by electronically altering the relative phase of the different transducers, you can electronically steer the area of interest or the area of observation very, very quickly. And you can also do so with a flat array that doesn't require you to take a large reflecting dish and move it. It's much lighter, it's cheaper, and it's infinitely faster. The reason I don't think that they're depending on a phased array is simply because all of the models that you see out there have the same sort of yoke design and ability to steer. You wouldn't add that if you had the ability to do it electronically. Finally, if we get into the phasing relationship, what happens with phase and sound, I think it'll become pretty obvious to you that I think the phasing operation or the phasing of these devices is a secondary effect. Before we get into that, though, I want to talk a little bit about speakers themselves and what's being done to produce the sound. The two most common types of speakers out there are horn speakers and cone speakers. Cone speakers are the type that you see with the diaphragms. They have a membrane in front driven by an actuator, and a horn depends on the geometry of an expressing horn that sends the sound outward. The Voight speakers that we built, they depend on a cone type of speaker. The distributed mode loudspeakers that we built, as well as electrostatic speakers, are kind of an outlier. They're pretty uncommon and they're not very often used. The horn speakers are typically used for megaphones and for public address systems because they are enormously more efficient than a cone speaker. But the reason they are is because of a property called impedance. When you take an actuator, let's say for example, this is an example, a horn driver, but it applies to both a horn and a cone. What you have is a coil of wire inside of a permanent magnetic field and then electrical connections that allow you to induce a current in the wire. That produces a magnetic field, and depending on the polarity or the direction of the flow, the coil will either move forward or backward. And as it does so, as it moves forward, it will compress a thin layer of air in front of that actuator. And when it moves backward, when the current reverses and it moves backward, it will produce a rarefied node. And these high pressure and low pressure waves will move away from the speaker at the speed of sound, 330 meters per second. And they form a continuously expanding spherical shell around the speaker that will move outward at the speed of sound. And it's important that you understand that it is a shell of sound. It isn't directed, it's just expanding outward. And when I say high pressure and low pressure, I mean actually higher and lower air pressure. If you measure the pressure inside the peak, it's slightly above atmospheric, and in the troughs, it's slightly below atmospheric. The problem is that the air that this heavy transducer is moving is so light that you have very poor impedance matching. Impedance matching is the same thing as energy coupling. If I take a sledgehammer and I hit a ping pong ball, no matter how hard I hit it, I'm not going to transfer much energy, much momentum to that ping pong ball because it's so light compared to the head of the hammer. In order to get more efficiency out of it, what I could do is I could take that hammer and I could slam a bag full of ping pong balls, thousands of them. And that's effectively what happens with a cone speaker. By connecting the driver to a membrane that increases the surface area, it increases the number of molecules of air that are going to interact, that are going to be pushed by that motion of that tiny little actuator. And so effectively, I will couple more energy into the atmosphere. However, there's a more efficient way of doing that, and that is to use the geometry of a cone. What happens is when the tiny little actuator moves at the back of the cone, all of the air in the cone is constrained within the cone. And so we have a much larger mass because the air can't get away from the sides of the cone. And so when the air finally gets to the end of the cone, we've coupled a lot more energy into it. Just the same thing as if I took a sledgehammer and pounded the end of a pipe that had thousands of ping pong balls in them. They all have to respond to the hammer, and I'm going to get even better sound coupling. I'm going to demonstrate that right now with this setup right over here. Now what I have is our tried and true amplifier. I have our signal generator over here. I have one of our concrete cone speakers, And then I have a typical horn speaker located over there. I have a little decibel meter and a meter stick so we can measure the distance. Now when I turn this speaker on, I'm going to fire it up at 1000 hertz. And I hold this decibel meter at a fixed distance in front of here. You can see that the output on the decibel meter is about 82, 83 decibels. Now if what I do is I turn off that annoying sound, I don't adjust anything else, but I just replace the wires and I drive this. Fire it up. You can hear the difference. And if I hold this like this, you can see that we're at least 10 decibels louder at 1000 hertz. Now, you might think, well, okay, maybe it's more efficient, but maybe it's because the sound is being directed right at the meter. That's not true. Even though there is a directionality, this does tend to be more directional. Nevertheless, it's the impedance matching that matters more. So what I'm going to do is I'm going to hook up with the same settings the driver for that cone right here. Now what I'm going to do is I'm going to aim this away from me like this. So the sound, if anything, is going to be projected in this direction. Listen carefully to what happens when I put the cone in front of it and increase the impedance matching. Much louder, much quieter, even though I'm sending the sound away from me. The impedance matching is more important than the directionality. These horn speakers are at least 10 times as efficient as these cone speakers. Now you might think, well, okay, if that's the case, why do we ever use these speakers? We could use much smaller amplifiers, produce a lot more volume, less power usage. Great, right? Well, it's true, technically, that a horn speaker is always going to be much more efficient than a cone speaker. But for you audiophiles out there who say, no, that's not, it is true at all frequencies, but there's a deal killer issue, and that has to do with scale. What happens with a horn is that when the tiny little actuator is moving back here, as the frequency continues to drop and the wavelength continues to increase, eventually you get to a point where you can't even get half a wave across the opening of the speaker. At that point, what's happening is because the actuator is moving so slowly that during the beginning of a positive pressure pulse, the air is beginning to move out of here and beginning to spill out of the end of this while it's still moving forward. The cone is not containing the mass of air that it would have at a higher frequency. And so the only way that you can continue to have the beneficial efficiency of a horn speaker at lower and lower frequencies is to increase its size, and it's linear. This particular horn is rated down to about 800 hertz. That's where it really starts to lose its effectiveness. If I wanted this to be good to 400 hertz, I would have to make it twice as big in both dimensions. If I wanted to go to 200 hertz, 100 hertz, eventually if I wanted to go down to, say, sub-frequencies, 50 hertz, the horn would have to be as big as this room. So you can't really use these at low frequencies. However, when you take a cone speaker and you say, well, I'll give up the efficiency and I'll just use the cone speaker for everything. The problem is because this actuator, this driver, is driving a very, very tiny little element. It's very light. But when you start to produce, build a structure with a large membrane across the front of it, it's more massive. It takes longer for it to respond because of the greater inertia. So when you start to try to drive a cone speaker up to higher and higher frequencies, the inertia of the cone itself will start to cause distortion. And in order to couple to a lot of air, if you have a big cone, eventually the actuator is moving fast enough that the flexibility in the membrane causes it to ripple. It actually isn't operating as a single unit. It's more like a distributed mode loudspeaker. And so you get different parts of the speaker actually producing positive and negative phased sound. Terrible distortion. So that's why typically these speakers will use a cone and a horn integrated into the same speaker cabinet with a crossover circuit that will effectively direct the power to the speaker that can best handle that frequency and to cover a broad frequency range. Just to prove that I'm telling you the truth, let me show you what happens when we do the same test with the decibel meter, but we change the frequency way down to 200 hertz, as I've got this set up right here. I've got the horn speaker wired in, and I'm going to measure the amount of sound output we get. About 56. Now if we hook up the cone speaker, about 63. So this now becomes louder. This was 10 decibels louder before. This is now about 5 or 6 decibels louder than its partner. Now the reason that we selected to only use the horn speakers is because the typical LRAD deterrence frequency is around 2000 hertz, which is just about the peak efficiency of the horn speakers. In addition, the LRAD system is also used for a PA, but it doesn't necessarily have to produce quite the level of volume, and it still is in the range where these things become pretty competitive. And the horns also have a little bit more directionality to their sound output. That's why I'm pretty sure that all of these units are also using a horn type speaker. Now, one thing you may notice about these speakers is that they typically tend to be a lot thinner than the device that we built here. And part of that is because they use what's called a folded horn. Effectively what happens is rather than putting the actuator, the driver, behind the horn, what they do, like you see in most megaphones, is they put the driver on the front of the horn, send the sound back to a reflector plate, and then reflect it back out in an annular pattern around the driver. This allows you to have the same distance, folded in half, and the same opening area, but you have half the thickness of speaker. The only reason we went with the system that we did instead of using that more compact model is you can't get very, very high power horn drivers that are folded as inexpensively and readily as you can these. And so that's why we ended up compromising and making the device a little bit bigger. So what I'd like to do now is talk to you just a little bit about amperage or current. What happens with speakers is that they are often rated according to their maximum power output, also their resistance, their ohmage. And most domestic speaker systems use 8 ohms as the reference resistance, so that you have 8 ohm speakers. The amplifiers are rated at 8 ohms. And what that means is that if you put an 8 volt charge or potential across the speaker, you will get 1 amp of current flowing through it. Put 16 volts in, you'll get 2 amps coming out of it. And that resistance is actually what determines the maximum output for an amplifier. So if you have a 100 watt amplifier, like our little amplifier here, rated at 8 ohms, that means that when it puts out about 28 volts, it's going to allow about 3.3 amps of current to flow through it. Because most domestic systems can take advantage of the higher available voltages, 110 or 220 volts, they can use then thinner wires and thinner components because they're not driving so many amps. The difference is that with the type of system that we got for portability, it's based on an automotive system, they don't have that same sort of voltage availability. They're limited to 12 or at most 24 volts. And so they give up that advantage in terms of the light weight simply to have a simpler electrical operation of the amplifier circuit. You can, however, drive speakers that are different than the rated output for your amplifier as long as you're cognizant of the maximum current that it can handle. So if this particular unit can allow about 3.5 amps through, but you drive a speaker that's only 4 ohms, it doesn't know that you have only 4 ohms of resistance. So if you crank it all the way up to full power, it's going to put 28 volts across that speaker, and you're going to get about 6 amps going through, and you're going to blow out your amplifier. But if you simply don't drive the amplifier any higher than a 3 amp output, or a 3.5 amp output in this case, it'll be fine. It'll work, but you only get half the power output. If you want to get the full 100 watts, you could take 2 4 ohm speakers and wire them together in series. So in other words, send the power into one, bridge over to the other, send the power back, and both speakers will then be seen by the amplifier as an 8 ohm load. And so you can get the full 100 watts out of it. And you can mix and match. You can take 8 ohm speakers and turn them into 4 ohm speakers by putting them in parallel. You can create 2 ohm speakers by putting 4 8 ohm speakers in parallel. So you have a lot of ability to manipulate the current limits on your system based on how you wire up the system. And I'll show you why we did that, or how we did that in this unit. So what I'd like to do now is I want to take this apart and show you how we put this together. Okay, so if we look at the outside of the box, you can see that it's mounted on this articulated yoke. And the yoke can be built out of any kind of material. We just have a lot of this 80-20 material available, and it looks nice and it's easy to construct, and you can reuse it for multiple projects. But the way that this is installed onto the box is that once I finished the entire speaker system and mounted everything on it, and I knew exactly how much it was going to weigh, then I simply took a little dowel rod, placed it underneath here, and rolled it back and forth until I found out what the center of balance was for this. Drew a line up, and then marking halfway across the height of the box, at that intersection I placed the pivot point with this heavy bolt and a plate behind it. As a result, I don't need a lot of resistance in this yoke, so that even when I turn it like this, it's not very difficult to move, but because this heavy box is well balanced, it doesn't tend to drift when you set it up. And then simply mounted this on a large post that goes into a pivot in our tripod that allows it to rotate. Now, if you look at the back here, you'll see the amplifier. Everything that we've got in here is from the company Orion, and they make some pretty good stuff. It's probably not the very best quality, but it's incredibly inexpensive because it's based on automotive, huge scale manufacturing. And so this small little amplifier, which is driven by only 12 volts in, sends out as much as rated 4,500 watts. And there's been a couple of videos where they've actually looked at this at the operating voltage from a battery, and they can get nearly 6,000 peak watts out of this tiny little amplifier. The power that comes out then is sent to the speakers through these wires here, through some watertight fittings in the back of this fiberglass box. And then on the top of the amplifier is easy access to a few controls, as well as a couple of RCA fittings that allow you to hook up a phone or a signal generator or a microphone or whatever you want to use to send the power in here. Now, if I take the back of the box off, simple fiberglass plate, this is bandsaw type of manufacturing with a little bit of sandpaper, you'll see the 4 very large cone drivers by Orion that are mounted from the front, which I'll show you in just a second. Each one of them is hooked up to the amplifier, and in this case, because these are 8 ohm drivers or speakers, and because the rated output from this amplifier is 4 ohm, we effectively run 2 of these drivers in parallel, so they become apparently 4 ohm loads, and then left channel, right channel, and we're always driving both channels in this stereo amplifier. You'll also notice the pivot points have back plates here. This provides a lot of support because this is a very heavy box. Each of these amplifiers weighs about 7 kilograms. So with the weight of the box and all of this apparatus, you're talking about a 50 kilogram, 45 kilogram system. It's very heavy. Nevertheless, you'll also see some of this fiber fill that we put in front that just helps to reduce some of the radiation of sound that comes off of the aluminum horns in the front. And then a pad back here that helps to protect the operator from any kind of reflected sound that comes back from the front plate. If you come around to the front of the speaker, pretty straightforward. We simply took some of this 12 millimeter or half-inch fiberglass plate and cut a piece that fit exactly within here and set it back about 3.5 centimeters back from the front surface. And then to that, we mounted the aluminum horns that bolt onto that plate. That plate has to be very strong because the horns are actually supporting those heavy drivers in back. And then because we set it back, we just glued in a couple of these little blocks in order to support this aluminum, perforated aluminum grate that just protects the speakers and allows the sound to come out without any kind of resistance or obstruction. And then finally, the system itself is very robust and it's not going to be damaged by falling or anything like that, but it isn't waterproof. It's obviously vulnerable if you were to really throw a ton of water in there. But remember, we're only dealing with 12 volts. So that tends to be not, that dangerous in terms of operating at those power levels. You'll see the heavy cables that hook up to the battery down here, and you'll also see a lightweight connection here, which would normally go to the switch on a dashboard in a car. So if you had this permanently hooked up to your battery, you can then switch the unit on and off by providing a 12-volt potential through this small little lead here. So if we go around to the back, let me explain to you a little bit about power. Each of these drivers, if you look carefully, has a maximum peak power of 1200 watts. Now that's not what it can maintain for a long period of time. They would overheat very quickly. But for a chirp or a peep, it can handle basically the output from that amplifier, almost 5 kilowatts. RMS, they're only rated at 400 watts each. But sound is an interesting thing in terms of decibels. If you take these drivers, which are very efficient, and put 1 watt through them, they will generate, and we tested this, 120 decibels at 1 meter with 1 watt. And as you double the power, based on the decibel scale being logarithmic, if you double to 2 watts, you will get 3 decibels of increase. So if we increase from 1 watt to 256 watts, we will effectively have 8 doublings, or 8 times 3 decibels, or 24 more decibels than the base output SPL level at 1 watt. In other words, 144 decibels at 1 meter from one speaker. And that's conservative because that's not even the peak level. Now, a typical LRAD unit is rated at about 153 decibels at 1 meter. So you can see we're pretty much in the same range in terms of output. And this is very inexpensive. Each one of these drivers here cost $90 in a package of 4, and the amplifier was less than $100. So for about $500, depending on how much you want to spend for the fiddly bits, you can build a very powerful sound projector. And it's very simple because everything is from the same company. It's just plug and play. All you got to do is you just have to have an MP3 player or a phone or some source of, even a microphone, some source of sound, and you can get a tremendous amount of sound out from the other side. Now, I said I was going to explain a little bit about phasing, and the reason phasing is important is because it's not really discussed in terms of the safety of these devices. When you take 2 speakers, and I'll try to help you to visualize this because I don't want to do a lot of drawing here. If you have 2 speakers that are sending out sound waves and you're equidistant from both speakers, and they're sending the same speakers, same frequency, and you're the same distance from them, when the sound pressure waves reach you, they will reach you at the same time. So you will experience a doubling of the pressure peak, and at the troughs, you will experience a doubling of the pressure drop, effectively a linear doubling of power. Typically, when you add multiple speakers to a system, you will increase the average sound pressure level by the square root. So if you have 4 speakers, you'll produce an average doubling of the sound output. This is important because as you add more and more and more speakers, you will increase the sound more slowly on the average than you do at certain specific locations. Now, as you add more speakers, those locations will become rarer and rarer, and so you'll eventually reach a point where they're very, very infrequent, like a few killer bees within a large field of mosquitoes. But those killer bees can be very dangerous because the pressure level can be far higher than the root mean square level that's rated from the speaker system itself if you just added them up as you would normally add unphased systems. If you have 2 speakers, each producing spherically expanding sound waves from the speakers, at a point midway between the 2 speakers, you're going to get these points of positive interference. And even if you're at a different frequency, you'll notice here the spaces are narrower, therefore this is a higher frequency, and you'll notice in between you'll get these peaks located at certain locations here. However, what you'll also notice is that if you vary the location in the field, it's very rare that you're going to be finding that you're at a particular peak as more and more speakers are added, because it becomes less and less likely that you're going to be an integer number of wavelengths from this speaker and this speaker. Because I didn't describe this before, but basically you don't have to be exactly the same distance from the speaker. You can actually be just an integer number of waves from the speaker. So what happens is if you are equidistant from 2 speakers, say 3 waves and 3 waves, I'm going to get positive interference. If I'm over here and I'm 3 waves and 4 waves from the speaker, I'm still going to get positive interference. If I'm in between and I'm 3 and 3.5 waves, in other words, at a node, I'm going to get destructive interference and actually a reduction in the sound pressure at that location. As you add more and more speakers, the likelihood of all of those speakers being an integer number of wavelengths from me becomes rarer and rarer. But because the power, the pressure adds linearly, what happens is the pressure at those locations can become dangerously higher than the RMS output. As I'll show you on this diagram, if you pick a location, for example, in this example up here, we have at this frequency, at this location, which is 1, 2.5 inches up and about 0.4 inches over to the left side of this graph, that's a positive interference point between these two speakers. If we go down to the lower drawing down here and we look 1, 2.4 and over 0.4 here, you'll notice that at that same location, we're actually at a positive and at a node. So this speaker is at a negative pressure and this speaker is at a positive pressure. So at that same location, at this frequency, you're at a quiet zone. But at this frequency here, you're at a very loud zone, higher than the average sound pressure. Now, the likelihood of you being that unlucky individual who happens to be at that point where the sound pressure is far higher than the rated sound pressure is very, very low. However, that's only at a fixed frequency. You pick one, you get lucky. You pick another, you get unlucky. But if you have what's called a chirp, that's the typical LRAD sound. Instead of a pulsed beep, you get a chirp, which is weep, weep. The frequency during that pulse increases. It covers, it spans a spectrum of frequencies. And so those very small, rare points where the sound pressure is much higher will move around, will actually shift. And although they'll sweep past you very quickly, you have a very high likelihood at some point during that chirp being at a positive interference of a lot of different speakers at a much higher sound pressure. Now, in mechanics and in physiology, fatigue and damage thresholds are not linear. So for example, if I took a 10-pound weight and lifted it, I could possibly lift it 1,000 times. I might be very, very sore, but I could possibly do it. But if I took a 20-pound weight, could I do it 500 times? If I took a 40-pound weight, could I do it 250 times? And so on, till eventually, could I take a 1,000-pound weight and lift it 4 times? No, I can't. At some point, no matter how short the duration, the sound pressure can be injurious. It can be dangerous. And that's something to keep in mind when we're running these things at very high pressure levels. So I would advise you that if you're going to use a device like this, be careful because it can be a little bit more powerful than you might calculate on paper just based on RMS addition of the speakers. Now, in the next video, what we're going to do is we're going to take this thing outside and we're going to have some fun. We're going to bring it around a few locations and see what kind of reaction we get from people. So that should be a ball. And if you are curious about anything that I covered here or you have a comment, please leave us a comment because I read them all. And if you have a question, I try to answer them. If you like the kind of material that we're covering here, please subscribe to the channel because it helps us to grow and it helps you to get notifications, especially if you hit the bell and say all, to new videos that come up as we generate them. So I want to wish you a very happy evening. Stay safe, have fun, and we'll see you soon.